Hello, intermediate algebra students.
I apologize for being out today, but I am suddenly sick. I will hopefully be back tomorrow to clarify any questions that you have on this. But yesterday, we started talking about 6.4, which is on geometric sequences, and we introduced it by giving a definition and doing a couple examples. So feel free to pause this screen if you did not get the definition of this. But a geometric sequence is a list of terms in which to find the next term. You must multiply the previous term by the common ratio. So the big takeaways from this yesterday was that the pattern was multiplication, and we call that pattern the common ratio. We talked about an example, 2, 6, 18, 54, where the pattern was multiplying by 3, which that is our common ratio. Depending upon the class you were in, it depended on how many examples we got through in this first little section. I wrote down A already. Our pattern was multiplication by 2.2, and that's pretty easy to see by looking at this first set here. To go from 1 to 2.2, we multiply by 2.2. In letter B, there's not necessarily a multiplication pattern because the multiplication pattern would not stay the same every time. Instead, this is an addition pattern where we are adding 1.5 every time. So this is called arithmetic. Although we're not going to be focusing on this as much this unit, it is nice to refresh our memories about what that difference is. And the last one, which is the one I wanted to spend the most time on, is where we are trying to determine, again, is it adding or subtracting or multiplying, dividing. If you notice, it goes from a positive to a negative, back to a positive again, and then back to a negative. So it wouldn't be possible for it to add or subtract the same number. So then I might think, okay, what's the multiplication pattern? But going from 16 to negative 12, I don't know what that is off the top of my head. So there is this method for figuring out the common ratio by actually doing some division instead of multiplication. So I would take my second term divided by my first term, and you could plug that into your calculator, and it would spit out negative 0.75. I could do that again if I wanted to, and really I can do it with any two terms that are next to each other. 9 divided by negative 12, and it gives me the same answer. Could continue, negative 6.75 divided by 9, and that also gives me negative 0.75. And I could do it with my last one, 5.06, and divide it by the term in front, and it also gives me negative 0.75. So what this tells me by doing division is that this is geometric, and my common ratio is negative 0.75. That's the multiplication pattern in that problem. So as a reminder, you can do division if you're not sure. What we're going to get to next is the recursive formula, and that word should seem familiar from the first time that we did arithmetic sequences. What a recursive formula is basically following the pattern. Okay, it is annoying to write the equation of because it is just, I feel like, innate in us to follow a pattern, but we're going to use this formula, and I'm going to show you the formula in a couple different ways. First off, although it's not written here, every recursive formula needs to include information about a sub 1, and a sub 1 represents the first term. So that will change depending upon the problem. The second piece that the recursive formula needs is this rule, essentially. A sub n stands for the nth term. R stands for that common ratio, which is the multiplication pattern. And then the a sub n minus 1, that's that weird notation, but that represents the previous term. Okay, and it's going to be very similar to what we did last chapter, just a little bit different formula. So in this example, what recursive formula describes the geometric sequence? I need two parts. I need a sub 1, and I need a rule for a sub n. A sub 1 represents our first term, so I'm going to write down 8 as my first term. A sub n, I need to have my common ratio, and then I also need to have that a sub n minus 1. So all that is going to change in this formula is my common ratio. So I need to figure out what am I multiplying by to get from 8 to 12, 12 to 18, 18 to 27. And again, that's one I don't happen to know off the top of my head very easily. So I'm going to do some division to figure it out. I'm going to take 12 divided by 8, and that gives me 1.5. And you could check that to make sure that that works for all of these, but in fact it does. So my common ratio here is 1.5. I'm going to plop that into my equation. So now I have, this is multiplication, my first term being 8, and the rule a sub n equals 1.5 times a sub n minus 1. All this is saying is that I am taking my previous term and I am multiplying my previous term by 1.5 in order to get my next term. So I would start with the first term, and then I would know I multiplied by 1.5 to get the next term if I wanted to build this sequence. We're going to do a couple of examples. Here, write the recursive formula for the following geometric sequences. So again, I need to know what my first term is. And in my first example, it is 3072. And then I need a rule. And that rule, again, is going to look the same nearly every time, except for this number in front is going to be the R, or the common ratio. So I need to know, what am I multiplying by? Again, I'm not sure, so I'm going to take my second term and I'm going to divide it by my first term, and I get 0.25. So that's what I'm going to put in here as my common ratio. And this is my recursive rule. Let's do one more, and then I'm going to show you something that happens that's a little bit different. This guy down here. Okay, so recursive formulas are beneficial in that it helps us identify the pattern, but it's really hard when we want to find a particular term. So that's where we insert these explicit formulas, which help us find any term. And we can find any term by just plugging in the term that we want versus having to follow a pattern. So our explicit formula, which is given here, a sub n equals a sub 1 times r to the n minus 1, utilizes the nth term as a sub n. R stands for that common ratio again, which again is also known as the multiplication pattern. And then a sub 1 is our first term. And in a later slide, we'll talk about why this formula is the way it is. But we're going to just start with doing an example. It says, what is the 10th term of the sequence? Well, first, I want to know what is the pattern. Okay, I don't know off the top of my head what to multiply 8 by to get 12. So again, I can utilize that option where I take 12 divided by 8, and that gives me 1.5. That is my common ratio. Now I can write a rule because I know my first term is 8 and my common ratio is 1.5 to the n minus 1. This is the explicit formula. So if they were just asking you to write the formula, this would be what we would write. Just like in recursive formula, you could also write this in function notation as a side note, where instead of using a and then the little n, I can write a parentheses n to the n minus 1. So this would be function notation. I'm not sure if Pearson does that for explicit formulas, but if they do, that's what it would look like. Now we can utilize this formula in order to find a specific term, and here we want to find the 10th term. So if I want to find the 10th term, all I have to do is plug in 10 for n. And again, you could do this in either version that I showed you. I'm just using the little n one. So what I really have is 8 times 1.5 to the 9th. I would highly recommend just plugging that straight into your calculator the way you see it. But if you're going to do it step by step, remember order of operations say to do 1.5 to the 9th and then to multiply that by 8. When I type that into my calculator, I get 307.55, which doesn't make sense to get a decimal since there was decimals up in my original sequence. This next problem is more of an application problem dealing with exponential functions and geometric sequences, and this is where we're going to see the difference between the two show. So we're talking about the number of subscribers to a blog, and that number of subscribers doubles each week. And we'll talk about what that means. And then they say, how can the trend in subscribers be modeled? Well, first, we have to look over here at this picture. Because we often are given information in the images, and it says in the first week they had 5 subscribers. So if I were to create a table here really quickly, in week 1 I had 5 subscribers. In week 2 I am doubling that, so that would be 2 times as big, so that would be 10. In week 3, I would have 20 subscribers. In week 4, I would have 40. So every single time we are multiplying our number of subscribers by 2. There are 2 different ways to write this as an exponential function or a geometric sequence. A geometric sequence, the explicit formula, utilizes the first term and then the common ratio. An exponential function is a little bit different, although it looks similar. Y equals a times b to the x. A in an exponential function represents our y-intercept. So the biggest thing people usually pick out and notice is the fact that the exponents are different, and the exponents are different because of the fact that one of them has the y-intercept and the other one has the first term. So if I wanted to write a geometric sequence, I have everything I need. I know my first term in week 1 is 5, and my pattern is multiplying by 2. This would be the explicit formula for that geometric sequence. If I wanted to write an exponential function, on the other hand, I'm going to have to work my way backwards a little bit because I know what happened in week 1, but I don't know what happened in week 0 or how many initial subscribers I had. So if I am multiplying by 2 to go forward, I would need to divide by 2 in order to go backwards. So that would be 2.5. And the only reason I have to do that in this problem is because in this equation, I need that a to be my y-intercept. The B still represents our multiplication pattern. So I would still put a 2 there, and then to the power of x. Both of these equations can be used to figure out what would happen in a particular week. So let's say I was curious about what was going to happen in week 10. If I wanted week 10, I would simply, in both of these, plug in to the power of 10. In the exponential function, that's something I would just type into my calculator, and in the geometric function, I would want to make sure to do 10 minus 1 first. What's super cool is that when we type both of those equations into our calculator, we do end up getting the exact same answer. It's just getting them a little bit different way. So 2,560. Again, I just threw that piece of information out there. I'm not actually going to do that this second problem, but it's important to notice the difference, but that also how similar they are. So a exponential function uses the y-intercept, but the geometric sequence explicit formula uses the first term. Next, we have this question. The formula a sub n equals 1.5 times n a sub n minus 1 with an initial value of 40 describes a sequence. Use the explicit formula to determine the fifth term of the sequence. Okay, so they are using, a rule, a recursive rule to tell us some information. I know that this is recursive because of this a sub n minus 1, that is recursive notation. Then they tell us an initial value of 40. That represents our first term. So we have a sequence that starts at 40, and then it is multiplying by 1.5 in order to get the next term. So the next one would be 60. And then the term after that, I would multiply by 1.5 in order to get that. Now, I could, in this case, pretty easily continue this pattern in order to figure out what the fifth term is, because 5 terms isn't too bad. But they did ask us to write an explicit formula, so I'm going to do that. Our explicit formula, a sub n equals a sub 1 times r to the n minus 1. I know our first term is 40, and we know our common ratio or pattern is 1.5. If I want to know the fifth term, I just plug in 5 for n. Before I type it into my calculator, just because I worry about order of operations, I'm going to do that 5 minus 1, but then you can type this whole thing into your calculator to get the fact, I should have been writing a sub 5 the whole time, 202.5. Once again, you could have used the recursive formula to continue the pattern if you would have liked to. So that's it for today. I just want to re-emphasize that you, in this notes section, you learned 2 different formulas, the explicit formula and the recursive. As a reminder, the recursive formula also needs that first term or initial condition or value that they say. You can utilize both in a variety of different situations. If there's anything that you were confused about during these notes that you want to go back on, please rewind, pause, or send me some questions if you have them during class, and I'll do my best to respond in a timely manner, or I'll get to them on Wednesday. You have an assignment. It's a 6-4 assignment. The problem numbers will be on Schoology. The sub also has the problem numbers. If I'm hoping that they have the worksheet to pass it out, but if they don't, it is on, the numbers are on Schoology, but the assignment is on Pearson for you to get started on. I wish you luck. Have a great day.